Hello and namaste everyone. Welcome to lecture 36 of this NPTEL course on stochastic approximation. So as you remember, in the past week and this week we are looking at some variants of stochastic approximation algorithms that we studied in the past 8 weeks. Specifically we are looking at 2-time scale and stochastic recursive inclusion variants of stochastic approximation, right. In the previous week we looked at a particular problem, which is that of solving a linear system of equations when some of the measurements are controlled by adversaries, and towards that we looked at minimizing the L1 norm of the objective function, right, and the objective function involved in L1 norm, and then we tried to come up with a stochastic approximation algorithm to solve that objective, right. So in the past few lectures we have tried to come up with a motivation for why we need to look at a 2-time scale algorithm, and in particular look at a stochastic recursive inclusion interpretation of the algorithm, right. In today's class we will see that we will continue with that interpretation. In particular in the past lecture we saw that the limiting dynamics of this stochastic recursive inclusion interpretation, right, results in a differential inclusion. In the previous class we sort of showed that the driving set valued map for this limiting differential inclusion is Marchoud, which guarantees existence of solutions. In today's class what we will do is we will show that at least for this idealized DI the solution trajectories indeed go to the desired solution, and building upon that we will see how one can extend that convergence result to the original stochastic algorithm itself. Okay, so that is the plan for today. So let us begin with the formal details. So if you remember, we wanted to minimize Ax minus expected value of y, in particular the L1 norm of this, right, and the samples that we had access to were denoted in the following way. So at time instance 1 we have one coordinate index and an appropriate sample calligraphic y1, and similarly at time instance 2 we have I2 calligraphic y2 and so on, right, and we were under the setting where if at time instance n in equals I and this I belongs to A complement. Recall that this calligraphic A denotes the set of adversaries. So if I belongs to A complement, we have that I corresponds to a honest or a non-adversarial coordinate, right, and in that case this calligraphic yn is presumed to be an independent sample of the ith coordinate of the vector y. Okay, so the vector y and the vector y here are one and the same, right, and on the other hand if I was adversarial in nature, then this calligraphic yn and hence the ith coordinate of little yn could be adversarial. So recall that this little yn was used as a proxy for estimating, I should not say proxy, it was used to estimate expected value of y, especially for coordinates I which are non-adversarial in nature. So towards that we proposed the following algorithm, right. So xn had the following update rule and yn had the following update rule. In particular one can view this as to be, one can think of this as an update that has been that is inspired by the gradient with respect to this objective function, right, and if you remember in the true gradient we would have expected value of y here, and since we do not have expected value of y and since sign and expectation, right, do not interchange easily. So what we did was we had this separate time scale on which we estimated yn separately, right, and the update rule at least for all I which are honest, right, would be given like this. So there is a typo here, this should be yn plus 1 I equals yn I plus beta n times something like this, right, and so I think there is again a typo, this should be calligraphic yn plus 1. Alright, so this was the update rule. So again I would like to highlight that, okay, this set of adversarial coordinates is unknown, right. So even though it is, so if it was known, of course we could just discard the coordinates, right, but the challenge is that we don't know which coordinates are adversarial in nature and hence which coordinates are honest. So whatever I have written here is for the set of unknown but fixed honest coordinates. So this is the update rule that will be followed by them, right. So here notice that we don't presume the knowledge of which coordinates are adversarial and which coordinates are honest, right. We just plug in whatever is in plus 1 sampled at time instance n, right. So we look at the corresponding coordinate of yn. Now this corresponding coordinate, if it comes from a honest worker or honest coordinate, then of course this is in some sense a proxy for expected value of y of I. On the other hand, if in plus 1 could be I, where I is an adversary or I belongs to the set of adversaries, then this could be an arbitrary value. However, the nice thing is that whatever be the value, they sit inside the sign function, hence at least on a per iteration basis, the worst that an adversary could do is the flip the sign. Is this okay? So this is what an adversary could do in a worst sense. So now let us recall how did we propose analyzing xn's update, right. We said that xn's update can be written in this form, where h of x comma y had this interpretation, right, and this expression depends on expected value of y, right, and if this argument is non-zero, then this sign function here will either take plus 1 or minus 1 depending on whether this coordinate is positive or negative. On the other hand, if this value is 0, then the sign function is allowed to take any value between minus 1 and plus 1, right, and here again the sign function we allow it to depend on what this value of y that is provided as input over here. In particular, these coordinates are the ones that can be controlled by adversaries. So the interpretation here is that each time you come to x, the adversary could choose something over here, right, depending on how they want to derail the algorithm, right. So that was the set valued interpretation of what this h of xi means. I will sort of give the formal details on the next slide. And this epsilon n was basically the difference for I in A complement between the sign expression and the sign expression here, and there should be a AI as well, right, and in some sense this is the gap between what we would have ideally liked. Ideal here is with the knowledge of expected value of y of I, but this yn is what we have at time instance I. So we ask what would be the difference between these two coordinates, while yn goes to expected value of y, okay, this difference need not go to 0 because the sign function is actually discontinuous. So there is some challenge involved in analysis of epsilon n. Nevertheless, I mean the intuition is that because yn goes to expected value of y, we would be able to show that somehow epsilon n does not impact us that much, and mn plus 1 is basically what is the true update minus the sum of this quantity and this quantity, right, and one can see that by the way we have defined this mn plus 1 1, right, this expression will cancel off with this, so we will be left with this and this quantity, and hence one can see that mn plus 1 1 is indeed a martingale difference sequence. In particular, its conditional expectation is 0. Right, and here is the set valued nature that I wanted to describe. One can show that the limiting dynamics of this stochastic recursive inclusion, okay, is governed by x dot of t belongs to capital H of x, where h of x is given by this linear sum of these ai's. Recall that this ai transpose is the ith row of A, right. So ai over here is the transpose of this vector, right. So this is a d-dimensional vector, and we have some linear combination of such vectors, and we insist that for a given x, lambda I be the sign of this quantity if I is in the set of non-adversaries, right, and ai transpose x, okay, does not equal expected value of y of I. So if both these conditions are satisfied, then we require that lambda I be this sign. On the other hand, if either of these conditions fails to hold, then we allow lambda I to be any number between -1 and +1. So we consider all possible linear combinations, and if you go back, one can conclude that this little h of xn comma yn indeed belongs to capital H of xn at every time instance n, right. So whatever be this yn input, one can show that this will belong to capital H of xn, and this is why I said that there is a set valued interpretation to this update rule over here, which makes it a stochastic recursive inclusion, right. And you know, in our previous class we said, you know, this map H over here is merge out, right, and one of the first goals for today's class is to check if you look at this idealized differential inclusion, will the solution trajectories of this differential inclusion converge to the solution of this objective problem, right. So recall that the solution to this objective problem is indeed you know, is expected value of x, which is the true thing, right. So this is the true thing that we want to estimate, and this is the solution to this objective problem. One can show that by you know, by using the fact that our A matrix is you know, we presume our A matrix to have full column rank, okay. So we presume this condition. So under this presumption, one can check that, you know, the unique solution to this optimization problem is indeed expected value of x, okay. All right, so far so good, okay. Now let's, you know, try to see if this goal can be achieved, which is that, you know, can we show that every solution trajectory of this limiting di indeed converges to expected value of x or not. Towards that, we make use of a Lyapunov argument, which basically means that we show the existence of a Lyapunov function, right, and Lyapunov function basically says that along any solution trajectory of this di, the value of the Lyapunov function keeps decreasing, right, and it sort of keeps decreasing until you reach the minima of this Lyapunov function, right, and because of this reason, one can, you know, the existence of Lyapunov function itself guarantees that all solution trajectories of the limiting di would indeed converge to expected value of x, okay. So let us go over the details more formally. So we are going to define V in the following way, okay. So V is a map that actually goes from Rd to R greater than equal to 0, which means that the input to V is a d-dimensional vector and the output is some non-negative scalar, and it is defined in the following way, right. It is V of x is half times, so this is some normalization that we use to make our life easy, right, times the norm of x minus expected value of x, right, and the L2 distance between them and the square of that, okay. So this is how we define V of x. Right now, if you consider any element in h of x and take the inner product of grad Vx transpose z, right. So let us see what happens over here, right. So x minus expected value of x transpose z, right. So now if you recall h of x, the definition of h of x, one can, you know, presume that z has this following form. So z equals summation you know, 1 over n I equals 1 to n lambda I ai, okay. So z has this form where the lambda i's are sign of suitable quantities when, you know, your I is non-adversarial and ai transpose x not equals expected value of I. On the other hand, lambda I could be arbitrary. So keeping that in mind and keeping this expansion of z, right, what we do is, okay, what we do is we break this you know, summation into different sets of coordinates. One is where I does not belong to A, so I should say I does not belong to A and not I does not belong to A complement. I does not belong to A, and ai transpose x is not equal to expected value of y, collect all those i's, right, and there this x minus expected value of x transpose is as it is, and this lambda I ai, right, whatever we have is basically ai, and this lambda I should equal this sign expression over here. Is this okay? So that is exactly what I have written, right, and for all other i's I have written x minus expected value of x transpose times ai times lambda I, and this lambda I could be some arbitrary number between -1 and +1. So what we will do is, let us consider some I which satisfies these two conditions, that is it is not an adversarial coordinate and ai transpose x not equals expected value of y. In that case one can see that x minus expected value of x transpose ai, right, I can sort of since x transpose y equals y transpose x. So using this relation I can sort of interchange the position of transpose, right, and then I can use the linearity property and say that ai transpose x minus expected value of x is basically ai transpose x minus expected value of y of I. So notice that this expression is basically what this expression is, and whatever you have over here appears inside this sine function as well. So the argument to the sine function and what you have here, right, are similar in spirit except for a sign change. So notice that this expression equals this, and the negative of this is what is present inside the sine expression over here, right, and hence one can conclude that for such i's, for such I meaning those i's where these two conditions hold, right, the inner product between x minus expected value of x and ai times the sign of this, right, will equal the negative of the absolute value of this difference. So let me elaborate, right. So if you take x and multiply it with sine of x, my claim is that this equals the absolute value of x. So this is easy to check. If x is positive, right, then sine of x will be +1. So x times +1 will be x itself, and because x is positive it will equal absolute value of x. On the other hand, when x is 0, then this will be 0, and sine of x can be any number between -1 and +1, but in whatever value sin x takes, right, x times sine of x will be 0, and hence in that case also this expression will equal absolute value of 0, which is 0. On the other hand, when x is negative, so let us say this is -5, so this will be -5 times -1, which will again be equal to 5, right. So this part, if you understand, that will, you can immediately see that your one can immediately see that x times sine of minus x equals minus absolute value of x, right. So from this one can immediately see that the relation that we have over here, right, leads to this thing, that is minus the absolute value of ai transpose expected value of y of I, right. And in the same way one can see that if I belongs to a complement and ai transpose x equals expected value of y of I, which means the argument to your sign expression is actually 0, right. So in this case also this expression, okay, times this expression, okay, will equal 0, right. This will equal 0 because ai transpose x equals expected value of I for whenever such a thing holds, and again one can show that this equals minus ai transpose x minus expected value of y of I, right. So in this way one can see that for every x, your grad Vx transpose z for any z in h of x, so recall that z belongs to h of x, so this inner product can be written as minus 1 over n summation over I in a complement, the absolute value of ai transpose minus expected value of y of I, plus 1 over n summation I in a ai transpose x minus expected value of y. So let me elaborate what happened over here. Okay, so recall that this is the true equality. So what we have done is, for all such terms we have shown that this expression equals minus ai transpose x minus expected value of I. Here what we have done is, we have broken this sum into those which belong to I in A complement and this condition is satisfied, or I belongs to A. So we have sort of split it up into this two cases, and for this case also we have shown that this expression must equal ai transpose x minus expected value of y of I with a negative sign. I mean, for this case and this being true, right, this being true, one can see that this expression will basically be 0, and for all other I, all I am saying is that, look, whatever be this quantity over here, whatever be this quantity, this lambda I is a scalar, hence this whole expression is upper bounded by x minus expected value of x transpose ai. Okay, so it is upper bounded by this quantity. It is upper bounded by this quantity because lambda i's absolute value is at most 1. Hence this whole expression is upper bounded, right. Let me write it cleanly one more time. So it is upper bounded by x minus expected value of x transpose ai, right. So it is upper bounded by this quantity, and again if I take ai inside, I will get ai transpose x minus the ith coordinate of expected value of y, right, and this is what I have written here. So in other words, for the honest coordinates I have a negative sign and the absolute value, right. I should actually say that this is not equal to but rather less than equal to, and for the value corresponding to the adversarial coordinates, this expression is an upper bound to whatever we had before, right. That is this is an upper bound to this ai, so expected value of y of I minus ai. Okay, so let me be careful. So this was x minus expected value of x transpose ai times lambda I. So one can see that for this expression, whenever I is in A, this quantity that we have, this quantity is an upper bound to this quantity, and hence we have this upper bound over here, right. So finally one can, by some rearrangement, one can see that for any x, your grad v of x transpose z is actually less than this quantity that we have over here, right. And my claim is that this quantity, that is the one within the round bracket, is less than equal to 0 with equality if and only if. Okay, so I should emphasize that it is if and only if and only if, okay, your x, that is the argument that you have here, okay, equals expected value of x. So why is that the case? Okay, so first let us understand what was the assumption on A that we had made. I think this was made a few lectures back, right, in particular when we looked at a simpler variant of this problem where we had presumed that there was no noise and so on and so forth. So in that case, from that Fauzi, Tabauda and Digavi paper that I had shown, okay, this was the assumption on A. So what was the assumption? That for every x which is non-zero and for every k which is the subset of your row indices, right, whose cardinality is upper bounded by q, right, we require that your sum of ai transpose x, where I runs over k, right, and absolute value of ai transpose x, right, where I runs over k complement, okay, this left hand side should be strictly less than the right hand side. So this was the property of your A matrix, that is, this condition should be true for every x which is not 0 and for every k for which this condition holds, right. Now while your calligraphy k, which is the set of adversarial coordinates, is unknown, right, we have presumed that the maximum number of adversaries is at most k. So wherever your calligraphic A occurs, you can think of right, your A complement being k. So for that particular choice of k, right, and substituting x minus expected value of x instead of x, one can see that this quantity will be negative, right, this quantity will be strictly negative because of this condition, right, and whenever this is not equal to 0, right, we will have this strict inequality, and hence this quantity will be less than equal to 0, right, with equality if and only if x equals expected value of x. Of course, when x equals expected value of x, both these quantities are 0, in which case this whole sum will be 0. So one can see why this conclusion holds true, right. So from this what we have managed to conclude is that for any x and any z in h of x, capital H of x, so let me elaborate. So z belonging to capital H of x, one can conclude that this inner product is less than equal to 0 with equality if and only if x equals expected value of x. Furthermore, one can see that the objective function itself is non-negative for all x, and this equality holds if and only if x equals expected value of x. So recall the definition of V that is given over here, and from this is where we are making that conclusion that x minus expected value of x is greater than equal to 0 with equality if and only if x equals expected value of x, right. And furthermore, one can see that from this definition itself, as the norm of x goes to infinity, right, this quantity will also blow up to infinity, right. And since we have verified this condition and the fact that this condition holds true, one can conclude that V is a Lyapunov function with respect to this differential inclusion, right, and in particular it is a differential a Lyapunov function with respect to this point expected value of x, right. So you can see that V of x is 0 if and only if x is expected value of x, that is what this point over here means, right. And from that one can conclude that your expected value of x is actually a globally asymptotically stable equilibrium for this differential inclusion, and what this means is that if you take every solution trajectory of this di, then it has to necessarily converge to expected value of x as t goes to infinity, right. So that is the conclusion. So what this means is that at least for this idealized differential inclusion, I say idealized because there is no noise over here, for this idealized differential inclusion, whenever we presume that A satisfies a condition like this, then indeed your solution trajectories actually converge to expected value of x, right. So this is as desired, right. Now what we need to check is whether xn converges almost surely to expected value of x or not. So recall xn's are your iterates of your stochastic approximation algorithm, right. So so of course whatever we have studied so far we can build upon that, that is previously we studied what is known as the ODE method, right. In that ODE method what we showed was that under some conditions the limiting behavior of your update rule is governed by a suitable ODE, right. So there is a similar generalization in the context of stochastic recursive inclusions as well, which says that if your xn update is a stochastic recursive inclusion, then its limiting behavior is also governed by solution trajectories of this limiting di, right. However, in this in our discussion, okay, we will actually make use of a different result, okay, which we will refer to as the Robin-Sigmund lemma, right. So I will discuss this in the next class. However, for those who want to make use of some result like this, I request you to perhaps refer to this research paper by Professor Shalabh Bhatnagar and his previous PhD student Vinayak Yaji, who sort of gives some sufficient conditions under which the limiting behavior of stochastic recursive inclusions is governed by a suitable differential inclusion, right. And we had actually used this idea that is the connection between a stochastic recursive inclusion and its limiting di to actually discuss the almost sure convergence of this update rule that we have been discussing so far. However, that discussion is slightly more involved, and thanks to the TA for this course, Dr. Anik Kumar Paul, right, he suggested that we can perhaps use this this Robin-Sigmund lemma to instead prove the almost sure convergence of the result of this form, right. So we will actually follow that, because I realize that is actually very easy to explain and teach in class. So in the next class what we will do is we will actually make use of this Robin-Sigmund lemma to show the almost sure convergence of your stochastic recursive inclusion which we designed over here. Okay. So until then, goodbye, namaste, see you then, bye.